Well, let's have some mechanics and materials learning today. And I'm going to talk about shear stress. Now, the first thing I'd like to do is show you the difference between shear stress and normal stress. To do that, we have to take a look at my ugly mug here. All right, if you take your um, hands, put them together like this, do it, don't just watch me, do it. And you push inwards, what you're feeling, and I've got a force coming this way and a force coming that way, what you're feeling is normal stress. There's an axial load divided by the area, and the stress is perpendicular to the area. It's a normal stress. Now, think of moving your hands this way, up and down. I'm going to apply that force without letting it move. And so there's a force there, and the force divided by the area is the stress. The force is parallel to the area, and that is a shear stress. And let's get rid of this so we don't have to look at me anymore. So we've done quite a bit of looking at a beam that is under some kind of load, whatever. And then we take that beam and we cut a cross section out of it, and now we've got the beam, and we do a free body diagram. And if we did the free body diagram here, we'd be able to solve for A, B, A, and then if we used our equations of equilibrium here, we could solve for V and M. Now, when we were doing the normal stress, the bending stress at this point, we focused in on getting the M and used that in our stress equation. Well, not now. Now we're going to use the V and use that in our stress equation. And the V, or the shear stress, equals VQ over IT. So if I were to give this video a name, let's call it Q and T. And then in the next video, we could do some examples finding shear stress. So we're going to take a few moments to figure out what are Q and what are T. What is Q and what is T? All right. Let's come up with their names first. Q is called the first moment of the area. And T is equal to the thickness. So for that beam that I had drawn there, one of the next things we look at is the cross section. So let's take a look at, maybe we have a rectangular cross section. Rectangular cross section. And let's let this distance be h, and this distance be b, and that distance be h. To calculate q, we are always calculating it from the centroid. So we need to know where the centroid is, and of course for this rectangle, centroid is at h over 2. So in the normal stress, or in the bending stress, we used the y, and y was the distance from the centroid to the point where we wanted to calculate the stress. What that caused is it caused the stress to be different at every location along the height of the cross section. That happens for Q as well. So if we're going to find Q, we find Q for a point, and then when we find Q for that point, any arbitrary point up and down, when we find Q for that point, we can now find the shear stress for that point. So let's pick a point. Let's pick a point right here, maybe at 3/4 H from the bottom, 1/4 H up from the centroid, and we want to find the shear stress at that point, so we want to find Q at that point. Let me write it out in words. Q is the moment of the area about the centroid where the area is the area from the point to the outer fiber. The area from the point to the outer fiber. So I go to my point, and the area from my point to the outer fiber would be the area that I've just cross-hatched. You pick the point where you want to find Q, and you draw a little line, and you push all the area that is from that point outward to the outer fiber. So what do I mean by moment? It's not force times distance in this case, it's area times distance. So Q is area times distance. Well, for my example right there, what is the area? Well, area of a rectangle is base times height. The area from my point to the outer fiber is got a base of B. And a height, what is this height? Of H over 4. So there's the area. What's the distance? The distance is distance from centroid of beam, or centroid of cross section, or centroid, to the centroid of A. In other words, of this area. Of this area we're talking about. Where's the centroid of this area? It would be in its center. So, how far is that? Well, I would argue that it's halfway into the area. So from the centroid, I'm going to go up H over 4, and then half of this H over 4, which would be H over 8. So H over 4 plus H over 8 would be 3H over 8. That's the distance. There it is. The moment of the area, the first moment of the area, I'm going to put that in here. It's called the first moment of the area. Q is the first moment of the area about the centroid. Area is A. Moment is area times distance. Distance is D. And so for this one point on this rectangular beam, Q would be 3BH squared over 32. And that's only for that one point. So I've got 3 questions for you, and I want you to take a moment to answer them. Press pause. For this rectangular beam, where is Q maximum? Where is Q minimum? And what are the units of Q? I want you to press pause and come up with an answer for me. Okay, you should be back. Q is maximum at this centroid. If I took the area from the centroid to the outer fiber, I would have the biggest area I can get, and multiply that times the area or the distance to its centroid, and I would get the maximum value of Q. Where's Q minimum? Well, what if I went out to the outer fiber and said, I want to know what Q is out here? And I have to find the area from my point to the outer fiber, and I'm already at the outer fiber. The area would be 0. So Q would be minimum at the outer fiber, and it would be 0. One more point. When you have symmetry, as we do in this rectangle, if you can find Q at a variety of places going up, you have symmetry going down. In other words, we would get the same value of Q down here as we did we'd get the same Q h over 4 from the bottom as we did 3h over 4 from the bottom. All right, last question. What are the units of Q? Well, 3 doesn't have any units. B is inches. H squared is inches squared. 32 doesn't have any units. Units are inches cubed, or meters cubed, or feet cubed, or whatever. All right, one last thing. What is T? Well, I said T was the thickness. And thickness is equal to, at the point we want, at point, finding tau. Remember, that can go up and down. We could say, well, what is the shear stress here? What is the shear stress there? What is the shear stress here? What is the shear stress there? And so on. At the point, finding that we want to find the shear stress, T is just the x dimension. The horizontal dimension, or the x dimension, or maybe the dimension parallel to the centroidal axis. Ooh, slide up a little bit there, Ron. So for our example here, what would T be? And the answer is B. So this dimension for our rectangular beam is B. All right, before I stop, I'm not going to do this example, but I'm just going to talk a little bit about it. What if we wanted to find Q for the different points on this cross-sectional area? Step 1 would be to find the centroid. Step 2 would be to choose the point where you want to find the shear stress. Let's say we wanted to find the shear stress right here. Okay, well, next we would find Q and multiply the area times the distance from the centroid of the area to the centroid of the beam. And then we would use T, and T would be this dimension right here. What if we wanted to find the shear stress there? Okay, well, then you got to find Q, and you multiply the area times the distance to the centroid. That would give you Q. Area, distance, and what would T be? That would be T. One more fun one. Let me see if I can find a different color. What if I wanted to find the shear stress here? Well, first I'd have to find Q, and Q would be the area times the distance to the centroid. That would be Q. But what would we use for T? Would we use this value of T? Or would we use this value of T? And the answer is yes. We would use them both. So there's actually, if you calculate the shear stress here, there's a discontinuity. It jumps. So you would have one value of shear stress when using this T. And so it's like taking a limit. As you're coming from this way to get to this point, you use the smaller value of T. And then again, taking the limit coming this way, as you get close, you use the big value of T. So you actually get two values of shear stress here, and it's just a jump. It's a discontinuity. All right. Write down your summary. You should be taking video notes. You should be making a summary of this video, and you should be writing down questions, and we'll see you in class. Hope you have a nice day.